Hello, this is Yatin Batra, and today I'm going to present my poster on probing the chemical applications of light and matter interaction. At first, I have shown the characteristics and different parts of the electromagnetic radiations, and the characteristics listed here are the wavelength, speed, frequency, and amplitude, which are required to understand the molecular structure. Here is shown the electromagnetic spectrum arranged with increasing frequency from radio waves to gamma rays, and how these different parts of the electromagnetic radiations interact with matter. Now, first I have discussed the microwave interaction, in which we probe the rotation in molecules, which helps in calculating the bond length and isotopic substitution. And here I have considered the rigid HCl molecule and derived the formula for its moment of inertia in all the cases, in all the three rotational axes. With the help of Schrodinger equation, I have calculated the rotational energy levels that are possible in a rigid diatomic molecule and the transitions that can happen if this molecule absorbs a microwave radiations. And here, applications are being discussed when the HCl spectra is recorded. Its first transition is observed at 21.2 centimeter inverse. By putting its value in the formula, we can easily calculate the HCl bond length. Here down we have shown the carbon monoxide spectra, which contains the 13 carbon isotope and the 12 carbon. By comparing both the transitions of 13 carbon and 12 carbon and using the formula that we derived earlier, we can easily calculate the atomic weight of carbon 13 spectra. Next radiations I discussed is the infrared interaction, in which I have to analyze the dancing molecule, which is basically the vibration in covalent bond. You can see this molecule is how this molecule is vibrating, and this vibrating takes place in two types, that is bending vibration and stretching vibration, which are further of two types, symmetric vibration and asymmetric vibrations, and in plane bending and out of plane bending. You can visualize this by this animation given below. Next, we see that the covalent bond that vibrates will produce the electromagnetic waves. And when this IR radiation interacts with the electromagnetic waves, they form a coupled wave which has a high amplitude. And this high amplitude shows the peaks in the IR spectra. So here we see the vibrational transition level, and the rotational levels are coinciding the vibrational levels. And the typical IR spectra is shown here. We observe that the 4000 the range from 4000 to 1450 centimeters show the functional group region, and the region from the 1450 to 500 centimeter inverse show the fingerprint region. And when the transmittance is 100%, that means the molecule is not absorbing nothing, there is no peak absorbed. And when there is some transmittance, a peak is absorbed, and all the stretches that a functional group faces are shown here in different energy levels. So here is the typical spectra of a nitrile containing molecule. By getting all the information by learning all the information that we saw in the previous slides, we can easily recognize the molecule by seeing the IR spectra. And to let you know that H bonding and conjugation plays important and a major role in absorption frequencies in IR spectra. So now talking about UV visible interaction, in which the electronic excitations are understood. So here I have shown the absorption spectrum when a transition is occurred after the absorption of UV rays. There are several transitions like sigma to pi star, sigma to sigma star. These transitions occur at different frequencies. And the lowest energy transition is HOMO to LUMO. Beer-Lambert's law helps us to get a quantitative and a qualitative relationship between the concentration, molar absorptivity, and the absorption of UV spectrum. As I told earlier that different transition occur at different energies, I have shown here that between 100 to 200 sigma to sigma star is happening, and 500 to 600 pi to pi star is happening. The solvent effect is also shown here, how polar solvent affect the energy transition, and how the polar solvent in n pi transition causes the hypochromic shift, and in pi to pi transition causes the red shift. The spectra of phenol in the presence of ethanol and isooctane, that is polar and non-polar solvent respectively, is observed here. Chromophore and oxochrome. Chromophore is the one that absorbs the UV light and causes the electronic transitions. When an oxochrome is attached to it, its transition and its lambda max value increases. So this is what an oxochrome do with the chromophore when it is attached. Effect of conjugation is shown here, that ethylene, butadiene, and hexatriene. As we are increasing the conjugation, the energy levels are decreasing and the lambda max value is changing. So here we see the lambda max value as we increase the conjugation in molecules, the lambda max value is increasing. This is the visible spectrum, and we can see that how colors in carrot and tomatoes are seen. And this is the beta carotene molecule, that lambda max value is 455, and in a liposinus in tomatoes, which lambda max value is 475 nanometer. So in this wheel we can see that the molecules will look opposite to the color they steal from the color wheel, so the color can be easily analyzed. So the conclusions that are which we can say that to understand the basic mechanism behind the interaction of radiations of different frequencies in matter is necessary, and to imply it in various chemical applications. And rotational transitions in the molecules by microwave interaction can help us in isotopic substitution abundance we discussed earlier, and also in performing organic synthesis. And infrared radiations with molecules can help us in determining the functional group present in a compound, whereas electronic transitions can help us in determining organic molecules. Thank you so much.